In this video, I'm going to go over the review outline for Chapter 2. So, as in Test 1, the first thing is you need to know the prefixes. Milli is 10 to the negative 3, centi, 10 to the negative 2, kilo, 10 to the 3. If any quantity has this prefix, then you want to get rid of the prefix first. And then you also need to know the units for these common quantities: charge, potential difference, current, resistance, the time constant, and capacitance. There will be a question on the test relating to being able to plug in units and finding which equation has the correct units, as you can see on the practice problems. So starting with Chapter 19, this is a short chapter that does not have much math. It has a few conceptual things. So first of is the definition of the current, defined as the flow of positive charges. So when we draw a circuit, we always say that the current flows from the positive terminal, which is the bigger line. Oops, try this again here. And the current flows from the positive terminal to the negative terminal. So the current would be flowing clockwise in this circuit. So that's the way the current is flowing, but it's actually the electrons that are moving. So we should be drawing the current the other way, because the electrons are the free particles that can move. And then we have resistors. So the first thing here has to do with the definition of resistance, which is right here. So according to this definition of resistance, that it's equal to the resistivity rho times the length divided by the area. If you increase L, then it makes R increase. And if you increase A, then it makes R decrease. That's what these two things say here. So this would likely be a conceptual question, such as what happens if you double length or double area. Remember that the area of the resistor, we're taking it to be a circle, so the area is equal to pi r squared. So if you double the radius, it actually quadruples the area. Back to the first bullet here, since we're looking at the equations, we do have the definition of current right here. That goes with the first bullet. So be able to manipulate this equation to solve for any of the variables. The current is the charges that flow through per time. And then the next one here is, if you increase the temperature, the resistance increases. So this has to do with this equation right here, which we can pretend that there's an R here and an R here instead of resistivities. Since rho and R are directly proportional, the equation applies for resistance as well. So this one is the one that says that if you increase the temperature, which is this one, then the final resistance is going to increase as well, which is this one. The quantities with the subscript 0 are the initial quantities, and alpha is a constant that depends on the material that is usually given to you. So you should be able to manipulate this equation to solve for any of the variables, is what this says right here. And then the next thing is to use Ohm's law to calculate VI or R. So we have Ohm's law right here. Now I did write it here as delta V equals IR, but we also saw it as I equals delta V over R. You should know also conceptually that if you increase resistance, then the current goes down. And if you increase the voltage that's giving energy to the charges, then the current increases. And the next thing here is just a conceptual thing. We talked very briefly about devices that are placed in the circuit that can be ohmic or non-ohmic. So we showed a graph I versus V for that device, and if it's a straight line, then it means that this is an ohmic device. It obeys Ohm's law. And you did a lab on this, but the slope of the line is the 1 over R. Because if you plot I as Y and V as X, then your slope, what's left over here, is 1 over R. And if your graph is nonlinear, such as something like this, it represents a non-ohmic device, such as a light bulb or a diode, for which you cannot use Ohm's law for the whole device. And the last thing in this chapter is a terminal voltage. Now, the equation that we have here is delta V is EMF minus IR. I'll go ahead and write it here. So that is a terminal voltage, so you really want to understand what this means. So what this means is that we have a circuit and this here is what we call the battery. It consists of the EMF source, what's giving the energy to the charges, and an internal resistance R, little r. And then this battery is connected to a resistor R, which is sometimes called the load resistance. And from points A to B here is where you have this delta V that is given in this equation here. That's a terminal voltage. So that's how much voltage that you're actually getting out of the battery after there's a voltage drop across the internal resistance of the battery. So you could also write that, let's say that you went, let me actually just change the direction of this battery here so that this could be the long one and this can be the short one here. So let's say you go around this loop clockwise and you start here, then you've got the EMF, which is going to be a positive number. We're going to the right here. So that's an increase in voltage. And then you would have a potential drop across the internal resistance right here, using Ohm's law to get this IR. And then as we go across the large resistance, we have another potential drop. And then we're back to our starting point. So the sum of all of these potential differences equals 0. So basically, this part right here is delta V. This is what we're getting from the battery. So all of it should be transferred to the load resistance here. Right? This IR here should be equal in magnitude to this delta V. And finally, the terminal voltage is equal to the EMF when the circuit is open. So all that this is saying is that if you have a switch here and it's open, then there's no current that can flow through. So that means that if you go back to the terminal voltage equation, this is 0. That means the delta V equals EMF. So the last thing is, when you're given the voltage of a battery, right? If you have a 9-volt battery in your circuits, you're going to be given the EMF, because it's impossible for the problem to give you the terminal voltage unless it specifically says the terminal voltage is so and so. But if it just says there's a battery in the circuit, it's giving you the EMF because it wouldn't be able to give you the terminal voltage unless you knew what the current was, since the terminal voltage depends on the current. And last thing I forgot to mention, this equation, just be able to manipulate it. We have energy being lost as heat through resistors, so if you are given one of the three variables of delta V, I, or R, you should be able to use them to solve for power or solve for any of the unknown variables.